Okay, so we are going to touch on cryptography today. Um, and we're going to touch a little at the beginning, it talks about hashing algorithm. And I think that having a really thorough understanding of this is going to help you along the way because everything that we touch nowadays has some kind of cryptography technology implemented. So we will talk about various algorithms and then how to compare them. When you need to make a decision for enterprise, that's going to be important. So for the first part, it touches on hashing, and we know that hashing allows us to validate integrity of the data, as it's mentioned in the first paragraph. But hashing can is required when you are using cryptography. So we are going to do a lab today that's going to touch on hash and how we can ID the hash using various tool and then be able to crack password by doing hash analysis and also crypto analysis. Okay, so let's touch on some of the type um, of hashes. So we have SHA, or known as SHA, and there's version 1, 2, and then with the key length. So this is the standard that was provided by NIST in 1993. And SHA-1, when it came out, it was, and it's still being used, right? It's not like it went away, but this was around 2010. So it's fairly recent for the hash algorithm, and then eventually got updated to SHA version 2. And then under the version 2, we're going to use the SHA 512 today. So you're going to see, we're going to use hashcat to be able to see if we can break this hash. So, and you can see how the flaw on using just hash to protect your password compared to additional components for password protection. Then you have, so this was widely implemented, SHA-2 with Windows operating system and other operating systems. So you see this. And then for the SHA-3 family, that was the same size in your hash bit. And that was from size 224 all the way through 512. And sometime that you would see that the higher value here for the function, right? That we want to implement that for the security. So your hash function, you should select the length that's going to be higher. So like 512 or at least 256 and above. Okay. So let's go through some of the questions. So in our assignment, the first question, it says, what is hashing and what is the primarily used? What is it primarily used for? So this is a one-way process. Usually a hash function is a one-way process. We use it to validate data integrity. So when you save a file, it generates a hash value. Your operating system does that. And then when you modify it, it edits or modifies the actual hash value. So the original file compared to the unedited file have two different hash values, right? So that's how we can tell if the file has been edited. And when you're doing forensic, hashing is useful. And then also when we're monitoring data for data loss prevention or other things like data integrity, if someone has intervened and modify your data. You saw that in the first section of the note, it talks about file monitoring using hash. We would use hash comparison, and you can use something like hash ID to look at the hashes, the type of hashes, and then you can use generator to create hashes. There are many types, bless you, of generators. So we are going to use a tool today so that way you can be introduced to it. You can use OpenSSL. You can use a lot of open source tool to generate your hash. So it is just used for integrity monitoring, often used for that. And then in digital forensic, we want to use that to validate or verify data authenticity, making sure that the data is in its true state, right? When you present that in court, you need to also present hash information for the type of files that you have carved out using forensic tool. And forensic tool doesn't modify the actual file state, right? Because when you open the file, it changes the access timestamp and it modified the state of the file. So when you use a forensic toolkit, it doesn't do that. So it keeps the file authentic or in its state that's intended. So if you're investigating, maybe a fraudulent case that look at, data leakage, or modifying financial systems and things like that, we want to verify the integrity of the file. And then for number 2, it says, why was SHA1 SHA version 1 deprecated? And which SHA version is preferred today? It's deprecated due to the weakness of the algorithm, so the vulnerability. And the areas that we see as vulnerability is the hash collisions. So SHA-1 has been jeopardized. So we want to move on to the newer version, which is SHA version 2 or SHA-2. This is the preferred. And then you can refer to SHA version 3 and so on. But SHA-2 is commonly implemented because it is just better in security. It has less of a vulnerability. There's no 100% solution to anything in technology. We know that by now, right? We just want to use a stronger and a better solution that would fit for the enterprise. Any question regarding hash? Okay. I'm sure you've seen this in CIS 27 and other courses. But a lot of this is just going to be review, and then some of it you are going to be able to learn new things through the notes and the assignment today. So there's some example on how you can use commands and utilities. So in Windows, right, I think I did this for my classes, certutil hash file, and you can use like the NTO kernel executable to generate SHA-256. And then it's going to output a hash value like this for that particular file. So we can do that with PowerShell. And in PowerShell, you can use a get file hash with your file name that goes there, and your file has to exist, right? So file has to have already been created. And then you can add the hash type. So if you're using SHA-256, this is where you would add it. So the example of that is like this. See you the following week. All right, the next section referred to HMAC, or also known as MAC. Bye. This is used for packet authentication. It's useful for integrity check, but is it very strong? No, right? Because it is packet authentication. It's not true authentication. So there is some flaw in that. The example of this is when you're sending, it's going to calculate an MAC value from the plain text. And then when you send it, it's going to calculate the packets that's received over the network to do a match. So this is another way that we can make sure that what was sent is truly received, and using HAMC or MAC, right? Because you know that an attacker can stuff a packet, can modify your payload, can change, so there are tools to be able to do that. So in case you have sensitive data, you want to implement technology similar to this or this one, to be able to validate. Now, it doesn't give you confidentiality for your data. It's only gonna give you the verification that things that were sent is truly what's received. It doesn't replace digital signatures. So if you implement digital signature, it is going to have a record of it, so we can't repudiate, and it's going to give you confidentiality, right? So you can have it digitally signed. And then your MD, this was created by Ronald Rivas. Hash collision is where two input is identical, create identical outputs. So this is where you see with SHA-1 that it has hash collision problem. So if they can modify or substitute, so that way they can generate a hash output, and that's how we can crack it, right? So message digest is also vulnerable for that, for MD2. And I think the common one that we see is MD5, which is often used in websites. And also our system has MD5, like your operating system, but this is also very vulnerable. So we want to stay away from that, knowing the vulnerability. So for 3, describe how MAC provides data integrity. It uses secret key combined with the hash function to verify data integrity and authenticate the data source, ensuring only authorized party can verify it. So that way the receiver should be able to verify what was the hash and how the data is intact when it's received. And if it's not matching, then we know that the data has been modified, right? So it authenticates to the packet. Any question?
Was so cool. Then I kept thinking about that class versus this class. I know this is more niche, but that class also had a lot of younger people who looked like they just came out of high school.
Yeah, the Network Plus classes, you know, a lot, it's required for the associate degree, it's required for the certificate. Uh, and this class is the last of the analyst certificate. It's not included. This one is articulated with Fullerton and Cal State San Bernardino if you take the class. But it doesn't necessarily, it's not part of the main associate degree. That's why you don't see a lot of the population take it.
Yeah.
But definitely if you want to be an analyst, you need to take this class because it is built around CISP certification. And if you look at all the analyst job, that's a certification to get right now, along with the CYSA, and other, right? From ISACA and like auditing and stuff like that. But you know, so and this is the first time we run it, and the first time we run it is usually kind of low anyway. So next time around there will be more students coming into it. But yes. Yeah, my 40A is always packed.
It looks so big. I was like, oh,
Next, we're going to talk a little bit about block cipher. This is interesting because I think that you probably hear about blockchain, cryptocurrency. A lot of the things that we use now uses blockchain or block cipher. So we want to learn more about it as companies are implementing it. I know a lot of people are using it, whether through a service like AWS or, you know, a cloud service provider that offers CBC. But anyway, so we'll touch on that and we'll talk about the weaknesses, right? Implementation, we have to think about like the benefit for the company, but also its flaw. Its flaw and be able to fix the problem. And that's our business, is to look at the vulnerability and how to either accept it, mitigate it, right, improve it. reduce it, or completely not use it. Okay. One thing that I did not include in the assignment is your RIPE MD. I think we learned this in CIS 27. This is also a hash function, and there are different versions as you see with the others. This is not used in, it's not commonly used um, in a lot of organization. However, it is useful for integrity in case you want to use it. It does, if you want to have confidentiality, you need to implement symmetric or asymmetric encryption with it, right? Just not use it on its own. So let's go down the category of symmetric encryption. Because symmetric encryption is built for bulk encryption. Anytime that you see web encryption, it uses symmetric, meaning that the same key is used to lock is the same key is used to unlock, right? It's like locking your front door with your key, and then that same key is used to unlock your front door. Symmetric is like that. So if you have the key, you can lock and unlock, right? Asymmetric key uses different keys, public and private key. So one key is used to lock and the other key is used to unlock. Symmetric, the reason why it's used for bulk encryption is because it is convenient and it's fast. So this is why you see it used for stream and block. So we'll talk about the categories and the type of encryption. So it has high efficiency, right? We talked about how it used one key to lock and unlock. So it breaks down to two categories of symmetric encryption. Block, which is, think of it like a chunk where it groups it and be able to lock each group, or stream, that means one bit at a time. A lot of the web-based technology, you would see that it is stream-based cipher using symmetric encryption, right? So block cipher, the categories for this is triple DES. If you study for Security Plus, you probably have to touch on this as well. And DES. DES is the beginning in the 70s. That's when they built it. And then triple DES is the replacement of that. Okay. So the DES, the key length is very small. You see it as 64 bits and 56 bits. It's been jeopardized, so that means that later on, right, at the end of the 90s, we see the triple DES that was implemented, and the key length for this is higher. So you want encryption, even symmetric encryption, with the higher key length. So by last year, NIST had announced that triple DES should be retired and we should use things like AES, which is symmetric. AES is in your smartphone. AES is in your wireless encryption, like in your wireless router. You can find this mode for encryption in your administrative option for your wireless router. It's implemented widely. This was implemented, or it was created and used starting 2001, which is a long time ago, but it's still withstanding over time. I think Apple was one of the first company that integrated AES for cryptography when they rolled their OSs before. So you also see the key length 128, 192, and 256. If you're using BitLocker, this is your XTS AES cipher mode. Okay, so if you're encrypting Drive using BitLocker in Windows system, that is an AES technology. For block cipher, we know that it is symmetric. For block cipher, for the operation, what we see is it breaks it down to some areas, like the electronic code book, your ECB. This is an example of a block cipher mode. Okay. ECB uses the same cipher for each block of data, which is why it's flawed. And when you look at the example here, right, if we input a plain text It's going to use the key to lock it. So it's going to encrypt it. And this is the encrypted text. Then it's when we have a second block, which has different plain text using the same key, and it's going to spit out a different ciphertext and so on, right? Because it is symmetric. So you are going to have the same key. And then it's applying the algorithm the same for each of the block. So can you guess this? Yes, right. Prediction for algorithm just require processor and computing resources, right? Processor, time, RAM, and be able to do analysis on it. So ECB mode is not fully secure. And then if you're looking at an example that's provided with the book, so let's say that this is the original image. Applying the algorithm, what it's going to do is going to add in a pattern. So that way it's going to change it up for the encrypted mode. Okay. So if the pattern is predicted or guessed, right, it's able to break. So that means that we need to know what that is and how it's used in block cipher, but we shouldn't fully use it in its entirety. So ECB uses the same cipher for each data block, making it vulnerable to pattern analysis, because if I analyze it enough, I can predict its pattern. And if I have its pattern, then I can unlock, right, the block. A lot of times we talked about, key length. So key sizes is important. Sometimes key can be captured or cracked. So we want to make sure that our key length is adequate. But in this case, it just basically, to break it is going to be pattern analysis. And next, we're going to talk about blockchain, right? So using CBC, this is going to help you improve from ECB. A lot of acronyms in this field, right? CBC encrypts each block similar to ECB. It is a block cipher mode, but it's using unique cipher. So that way it is not predictable with the pattern. So one block is different than the next block and different than the third block and so on. So it reduces the pattern prediction, and so therefore it is stronger than ECB mode. And this is what you see with cryptocurrency. But let's go and look at it closely. So cipher blockchaining, we use this for data storage. When I give you guys a batch, the company that batches, they use this CBC. And so for this mode, right, we know that it encrypts using unique cipher. So for each block is unique cipher, and it's applying symmetric key the same. So the first block is encrypted with a random, it's random IV, so initialization vector along with the key. And then the ciphertext becomes the IV for the next block. This is why we chain it, right? So the value for the IV from the first block becomes the unique becomes the IV for the next block along with the key. So this is how it's going to be unique throughout, right? So last year, right, cryptocurrency faced attack, but and there are different areas in that attack that we need to look at. So this is an older technology. I think it's widely implemented now because, we're thinking about security and how encryption is used. But you have to know that CBC is very slow, okay, compared to EBC. So the risk behind this is the performance, right? but there's no 100% security in any technology, as we mentioned. So CBC mode operates sequentially, so it needs to go from one to the next, and therefore it's called chaining. And it offers no improvement in performance, like using parallel processing. So when we use parallel processing when we're looking at the server system that's processing this, it's able to utilize the core, the processor, let's say that it's 32 core or even higher. It's better performed because all of those 32 core can concurrently working, right? So the code that they use to do that can be parallel process. However, CBC does not support that. So this is why we see deplete in performance and it's very slow. Now, the newer block ciphers do have some performance improvement. So this is what you see in the later sections. All right. So coming back here, we can say that CBC mode improve upon EBC because it uses unique cipher. We mentioned that. And for number 6, we talked about how symmetric encryption is suitable for both. It is faster. The key length or size is much smaller compared to asymmetric. It is efficient for large data volume. The reason why we use it for the web data is because web data is unpredictable. Web data is variant. That means that web data can be large at some point, right? You can have a lot of people downloading, uploading, people, transferring data in and out. And then there are times that there's very low usage of it. So in order to meet the need of web encryption, we often use that with stream, where it is able to handle bulk data or a small amount of data in any way. Symmetric is useful for that because it is convenient. It is just smaller in the key size, so it can be fast processing, and that's the goal. Compare that to asymmetric. It uses larger key sizes for sure. Ultimately, you have 2 keys, the public and the private key, and your key length is much larger. That means that it requires more processing power, more resources, RAM, and storage. It would then be slower in the case that if you compare symmetric to asymmetric. So it is not suitable for bulk data processing. Okay. So in asymmetric encryption, we know that we use a public and a private key, right? You would use one key to encrypt and the other key to decrypt. That means that when you set this up, you have to generate 2 keys. So already in that process, we already know that the 2 keys needs to be transmitted or stored. So the resources that require for asymmetric encryption is higher, right? There's higher requirement. So if you have large data sets, if you have big data, asymmetric is not ideal, because then you would utilize at least 50% more in resources in most cases. Okay. So a lot of the times when you, in general, right, like you see textbook answers or when you talk to people, they always say that encryption is the solution for security for most things. But lacking the knowledge in what type of encryption that you implemented is going to be deficient in that area, knowing that different type of encryption has vulnerabilities and also require much more resources. So whenever that you touch encryption, whether it's symmetric or asymmetric, it requires resources no matter what. So when we say use email encryption, 2 things is going to come to mind. One is going to be resources that you need to implement to support email encryption, second thing, it's gonna be slower. Okay, so you have to weigh the risk in what type of decision that you implement for the enterprise in security solutions, and that's important to think about. In general, yes, it does provide security, but right, you have the dot after that, but you have performance issue, but you have resource requirement, and then you got the maintenance behind it and the support. So there is no magical security solutions, right? When we accept something or we integrate something, we have to look at the advantages and the disadvantages for all things. All right. Output feedback, your OFB, this is a block cipher and it behaves like a stream. Okay. It's able to do parallel processing, which is faster than what we see with CBC. So performance is advantageous if you're using OFB. So this is what you see. You see also IV, the initial IV is gonna be input with the key in order to encrypt, output the encrypted text, right? And then you have the subsequent blocks. So the next step is going to be running parallel after the initial block. Okay, so it is faster. So you see this being implemented now for cloud storage quite a bit and cloud systems. So because on the cloud system, you would see that they have adequate processing and storage, right? Depending on the service that you acquire. But if you get top of the service, you're able to implement OFB. So it's newer. And then your CRT mode, performance over blockchain, yes, right? It's similar to what you see with OFB. It acts like a stream. So whenever you see stream cipher, that's fast. So anything that behaves like a stream cipher, that means it's gonna be quick. So there's some preparation requirement for CRT or CTR before it starts. You need to have a powerful system to take advantages of parallel processing. So OFB and CTR require more processor core. Okay. Slightly different than the last, you have the nonce. Okay. And I think in 27, we also touch on GCM. You've seen this before in another class. This is an implementation ideal for web applications, SSL and TLS technology. Now, they recommend to support authenticated encryption associated data, your AEAD, but it's still using MAC in the back, your message authentication code, through the packets. So here it talks about how you can use this to protect your data, right? They would try to forward the ciphertext to the server and then to attempt to decrypt that. And so that the system is going to try to decrypt that and send a reply. And they would use the reply to be able to gain access, because remember that this is through the packet authentication. So ideally they can do this remotely through, the technology. So AEAD ensure that your text is trusted and the proper MAC value is sent. So this is your GCM. Okay, and then the next part talks about Poly 1305. This is not part of your assignment, but this is also known using cha-cha, right? And you see cha-cha, they have cha-cha and salsa, right? So the creator for that's cool about this industry is if you create the technology, you can name it anything you want, right? So Poly 1305 is popular using Mac. It is also integrating AES. So it's known as Poly AES or Poly 1305 AES. Now it supports AEAD, like what we just learned. In addition to this, you want to consider additional options when you're working with these technology, right? A sole solution is not always ideal. So if you're using a certain hash algorithm, you want to couple it with the proper encryption algorithm. So to make it right, as long as they would be able to work together. Okay, so we haven't gotten here yet, but the question 8, it asks you, what is the main advantage of your ECDSA over the traditional DSA? It is just comparable in security, but the size of the key is less, it's smaller. That means that there's less computational overhead and resource usage. So whenever that you see less in the key length, that just means that less processing that we require, less storage that we require, like RAM, right? So processor always require RAM to be able to execute things, to perform a task. So what you see is ECDSA is better than traditional DSA, and we'll touch on that section next. Okay, so the next section talks about stream cipher, and as we mentioned about Cha-Cha in the last one, Cha-Cha is high performing. Now, stream cipher came around since Ron's code version 4, right? RC4. And then later on, that kind of went away because there's flaw in that particular algorithm. So Cha-Cha is a stream cipher. And it is real time. It, as I mentioned, stream is faster, so you see this for real time applications. A lot of it web-based application implemented stream cipher algorithm. It is an alternative to your AES deploying SSL TLS. So whenever you see this, that's HTTPS, encryption for HTTPS. So web-based applications. So if you don't want to use AES, Cha-Cha is an option. It does 20 rounds encryption with 256-bit key length, so it is strong. Now, the strength is gonna be the speed. That means it's fast and it's also not vulnerable to side channel analysis. Okay, so it does withstand. Now, Cloudflare adopted this. Google adopted it with TLS version 1.3. Then you have the Salsa 20. Same person, Daniel Bernstein, developed this. And it's similar to what you see with Cha-Cha cipher. The key length, there are 2 sizes instead of 1 compared to Cha-Cha, right? You got the 128-bit and 256-bit key size, and it is newer. I'm sorry, it's not as new compared to Cha-Cha. Okay. Then for the asymmetric, we're very familiar with RSA. RSA is everywhere. So when you're using SSH, right? SSH implemented RSA. So when I'm trying to connect to a switch using a terminal connection, like using PuTTY, I would be able to authenticate using SSH, and SSH require RSA. that means that I have to generate the keys to be able to go through the authentication. Now I can store the key, I can, you know, transmit the key, however that I want to protect the key. The keys are what is the requirement for the security. If your keys are jeopardized, then your encryption is jeopardized in symmetric or asymmetric, no matter what, right? So, but the asymmetric keys, um, or asymmetric encryption would stand key capture a little bit better. It would consist of two keys, and you also have the key sizes in much larger, right? We are buying time when we're using this, but you just learned that when you're using longer key sizes or bigger key sizes, it requires overhead, right? Your processor requirement is higher. Here's your DSA, which is your digital signature algorithm. We know this. Earlier it mentions about digital signature. I'm sure you use this. I use this a lot to be able to have authenticity when I'm sending documents and things over email. So you have a sender and a receiver. Bob, right, uses the public key, and then so for Bob to use his private key, signing on to his to the email, then Alice is gonna use Bob's public key. Okay. And that means that Bob public key has to be transmitted. That's digital signature. Okay. So you have to have a transaction of the key for DSA. Now that's the traditional DSA. And then when you compare that with your ECDSA, which is elliptic curve digital signature algorithm, elliptic curve is used for its portability and fast performance. Okay. So it's the same process with the standard key and the key distribution or transmission, uh, very close to your RSA as well. But the advantage of your elliptic curve, because it's small, it's petite, right? Like whenever I think about elliptic curve algorithm, I always think that it's portable and it's smaller. So the key size is going to be a 10th of the size of your RSA key. So this is why the preference for ECDSA is well above your regular DSA or RSA. So less computational requirement for the keys. Then your DH, this is for key agreement protocol. This is how you can have secret exchange of keys. We can use VPN technology like IPsec or IP security, or you can use SSL TLS. And SSL TLS requires certificates in order to have key sessions. And then your elliptic curve cryptography, your ECC, this uses key pairs and it uses algebraic equations, so mathematical implementation in the algorithm. They all do, but some of it, some of them uses random type of generation for the values with the key. But this one uses algebraic equations to create an ellipse and then plotting the points to generate the keys using mathematical processes, right? And then for the key agreements, it uses the key agreements and the digital signature. This is how the key can be transmitted or have a transactional for the key. And the key's length is 256 bits. I think this one is preferred by NSA or government agency for the performance purposes. And it is, you can break it, but a lot of times it is a little bit harder to jeopardize it, right? You can read the information in the standards. And then we have elliptic curve, your ECDH, which is combining the technology. and it uses ephemeral keys. So there is forward secrecy, and that's used for key, for how you can access the master key, right? So your key exchange, how you manage your key exchange is going to be the security behind this particular, for asymmetric key encryption, or even symmetric, right? Like I mentioned earlier. But this particular one, if you can gain access to the master key, you will be able to decrypt the session. So key should be changed and rotated. All right. So we learned about that. Let me go down, move 8 down so we can see 9. So for number 9, it says define perfect forward secrecy and provide an example of its use. And you can refer to that section of the note that we just went over. So a perfect forward secrecy, it ensures that your session keys are not reused or stored. So it's rotated and changed. An example of this would be your ECDH generates a temporary key for each session and preventing future decryption of the master key to be compromised. So it's harder to compromise the master key. So elliptic curve Diffie-Hellman encryption does this, right? And that's an example of your forward secrecy. It's a process for key exchange, and the keys are always going to be different. So for SSL and TLS, we see this is abundantly used for web technology, right? Anytime that you see HTTPS for the authentication, for accessing resources on secure website. So I think we should move forward with version TLS 1.3, but you do see 1.2 is still being used in some organization. So at least TLS 1.2 and 1.3 are recommended. This is for secure connection, and they support encryption algorithm that is modern, and that means that we have less vulnerability, right? I say less is there's not 100%. So that means that our security is going to then be improved. Is that okay? Did I forward too fast? We're good. All right. So we know that password is stored with encryption and hashes, right? Uh, when we create a password, it generate a hash, and it also in our operating system, encryption algorithm is used to encrypt shadow password or the storage of your password. So there are ways that we can improve this, because we know that if they're able to get the hash of your password, they're able to crack your password. So we can use an approach that's called key stretching, and this is going to help your password security. So that means earlier you saw that there was encryption algorithm that does 20 rounds, right? That means that it goes through, that requires processing power. However, the more rounds that you have, the better the security. So your key stretching just require more rounds, right? Multiple rounds of encryption. That means that it makes the brute force hard. So if I only have one round of encryption, if they brute force it, right? They would be able to crack my password. But if I have 20 rounds or 5 rounds of encryption, it just, we're buying time, right? They need to brute force it 5x over, 5 times over in order to get it. And that would just require hours, days, and months, or even year. So that's just time consuming, and it requires a lot more resources. Now, if they have more computing power, more systems to try to crack that same password, right? That's just going to speed up the process. But in security, we're playing game against time. So if you implement key stretching, that enhance security. How? It's just allowing us to buy time through multiple rounds of encryption. Okay. So there's SSL information on the bottom of 11, and it gives you the example, right? Through HTTPS, we see that there's confirmation for the TCP suite. But here with TLS, SSL and TLS, you have a pre-master secret key that is public, that's generated. And the server uses that key to decrypt. So that's the pre-master key that would then be received. Okay. So look at this diagram. So it breaks down all the process for SSL certificate, how that's used. Like I mentioned earlier, that requires a certificate, right? So we call this process the handshake. Now here it says, if there's no common cipher suite for the suites, both parties, then the cipher mismatch will occur. And so if you have a cipher mismatch, then the server will be confused. So your connection is going to be refused. Okay. And this is going to result in weak cipher suite. So what you see is that, instead of being able to respond, it's not going to be able to respond. So in the case if you have cipher mismatch. So that also means that it's not a perfect solution. And then there's your email encryption technology. I think we revert to some of the common legacy eventually upgraded for email. But we learned that MIME is a common protocol, right? That's protecting your inbox and your outbox. But a lot of your email, some technology uses asymmetric, but a lot of the email technology uses symmetric key encryption. So if you're using IPsec for VPNs, right? It does the HMAC, so the MAC hashing. It does symmetric bulk encryption, and it also integrate asymmetric secure key exchange. So even though it encrypt with symmetric, right? But for the key to be able to transmit or send the key, it uses asymmetric key. That's how you're supposed to do it. It uses asymmetric key for the key exchange process alone. Okay. IPsec is the preferred solution for VPNs for security reasons. I talked about SSH already. I think if you took my 40A, you've seen this. This is how we can connect to our appliances like switch, router, firewall, etc. And we can select SSH. In this case, we're connecting to router 1. And then on the PuTTY application, you can set up the rules on how you want your keys to be transmitted or exchanged, right? The type of algorithm you can use. So the application supports that. If you select a certain, like, let's say if I select RSA, then It's going to allow me to have the process in how I would be able to maintain my keys. Key stretching is here on page 14. And then the next part is your password salting. I think we also covered this in another class as a basic. But we know that password is brute forced, and we can use pseudo random. So when we say pseudo random, that means that it's going to have the same start value. Let's say that value is 1, right? 1 right now at 6:04 p.m., right? That it's going to generate it with the value 1. 2 hours later at 8:04 p.m., it's still going to use the same value. Now, in order to have a true random, right? Not a pseudo random, I can use system time to have a seed value to generate. So in the code, what they can do is they can integrate system time. So at 6:04, it's going to use the system time value for 6:04, and it's going to generate the characters, right? At 8:04, it's a different seed value because the system time is different. It's going to generate different characters. So in a truly random applications, or truly random algorithm, it uses system time. So whenever that you see a pseudo random, your seed value stays the same, like 1, for example, or 1,000, right? It is a numerical value that's implemented in the code itself to start, right? It's always going to start. Let's say I start at 1, and then it can be like 5 and 9 and so on. But 2 days later, it's still going to see the same. So pseudo random looks like a random value, but is not, right? Is pseudo random vulnerable? Yes, right? However, salt is a way that we can implement a mix of character into our password string and hash it. Okay. So it's like a way that we can stuff it and add number to it. So that way, or characters to it. So what you see here is you can add the salt to the password, and then you can apply the hash function, and it store it as a salted hash. So even if they have your hash, they cannot guess your password, right? They can, if they can guess the salt algorithm. But again, we're just buying time. Okay. Okay. So for 12, it says, what is the purpose for salting or adding salt to the password before hashing? It adds a unique string to each of the password, preventing the attacks like rainbow attacks, and making it just harder to crack your password with pre-computated hashes, right? Those are pre-guessed hashes that can be used. Remember what I said, if I can guess the hash algorithm, then I would be able to guess what would be your string, your plain text that's stored, right? When we salt it, we're just adding additional characters to the password, and then when we hash it, it's different than your original. So it's harder to guess your password or attack your password. Now, earlier we talked about blockchain, and I think the next section it goes over like the example of cryptocurrency for blockchain, or on how blockchain communication is established. Blockchain technology is older, right? It's widely implemented, like what we said, because of security. Blockchain is security. It is decentralized, so there's no one point that someone can access. It uses a digital ledger that is in different location, and each of the block hash links to the previous one. So you would have a chain in using the hash link. And so if I'm able to access one area, that means that I cannot have information in other areas. And that's the whole point in the digital ledger. And this is what's used in cryptocurrency. Okay. So it says nearly impossible. You can see last year there's already a breach for this. So uh never say never, right? It becomes a challenge when you say never in security world. So, but you have to have the control on the network. So if you have, certain level of access to the network, then that's the flaw, right, for blockchain. But you see it widely used for cloud-based system. Here it talks about password-based key derivation function 2. You might have also see this for Security Plus, right? But for CASP, you also know what this is, CASP certification. This is used SHA-2 hashing and SALT, and it uses longer characters for the SALT to protect the password. So the more characters we have, right, the longer time that would be for the to be able to crack it. And NIST recommend 10,000 cycles for the hash for the password SALT. So that's going to give you extended time. And there is the diagram for that, for the rounds. So you're still stretching your password using PBKDF2. Bcrypt and Blowfish is similar to this technology. Okay. But it also uses the SHA-2. I think you can integrate Bcrypt. I think I wrote a lab with Bcrypt one time, but yeah, you can find some integration, and you can also use the tool that has the proper command for a certain encryption algorithm. Okay. The next area would be quantum technology. I think quantum, there is still a lot of research in quantum technology. The computational power in quantum is expensive, right? This is why you only have a few of them around the world. Google owns one, IBM has some quantum, NASA uses quantum technology. So you do have a private sector organization that built their quantum systems. And then you have the research, right, for government and agencies that would have it. So quantum technology, why is it highly demanded? Well, it's used for many things because of its computational power. Quantum system can perform complex calculation very fast. And so it's able to break encryption algorithm quickly. So this is why it's demanded. Like RSA, right, which uses prime numbers for quickly solving mathematical problems. So if you can solve the problem, because ultimately any form of a computer is a calculator, right? And the same thing for a quantum system, it's just a very complex calculator that is well performed. So if we're able to have access to quantum computing, right, we can have results for calculations quickly. And if an attacker uses a quantum computing system, they're able to break encryption quicker, right? So that's why that section was included. But you will see more an increase in quantum computing usage, right, as we move along, because we're able to build, right, we as a nation able to build the technology that's needed. Any question? We're almost done. We have like about 6 more to go. Thinking of you today. They're asking for my final reviews. So Mesa is doing final review sessions. I think that you can have access to their calendar on their website, but they're gonna do. I suggested to them to do like quizzes, games, or gift card drawings, and they bought it. So yeah, so they're asking for that. I think math professors and science professors are participating by providing final review. I will have for this class I will also have final review, and if we don't have it covered in class, I'll try to make a video for it so you can look at it. But make sure that you go through the questions, right? Don't forget we have a quiz that's due. I opened it for a little bit longer because I'm guilty. I should have released it sooner, right? But I tag on chapter 9, which is the last chapter. So it's just a longer quiz, so I give you a little bit more time to go through it.
I was looking for it. I thought maybe like either restricted.
Oh, it was just on a different module. Did you see it? Okay, yeah. Yeah, I kept it on a different module because each of my module has a due date, and sometimes that confuses the student. When I change the due date for one thing, so I want to kind of keep it separately so that way you can just go to it. In the future, this class, if I run it again, if I teach it again, that quiz is gonna be broken down to 2 quizzes. I originally, wanted to write it as 2 quizzes, but so right now it's kind of late in the game to do that. So okay. As you already started looking at the next questions, but there's some example for quantum technology, and then the blockchain that we talked about earlier, right? How it uses the ledger, but you can look at the diagram. So the first block, this is considered a genesis block. Then you have the hash for that. And then it's going to use the previous hash to implement for the next block. That's how it's chaining, right? Remember the hash link that we talked about? So that's going to go to 2, and then it's going to link with the hash for 3, and so on. And this is a peer-to-peer based network. So all the new transaction is accepted. Then it's going to be added for the nodes. And the transaction is considered your block. So it added to your ledger. So if someone requested a transaction here, right, it is broadcasted across the network. Then it's validated with one of the nodes. So you would have like a peer-to-peer environment. So it's decentralized this way. And then for homomorphic encryption, this is on page 18. This is used to protect the data that is in use. That means that I decrypt a file and I modify that file. Let's say that it is an engineering file for a product that my company is creating. Yeah, so you would access it, encrypt it, and decrypt it. So if you have things like that, this is what you see with like patient data, intellectual property type of data. That's important, right? That will be accessed through the application service. and it should be considered. Okay. So homomorphic encryption. And then in the next part, it's gonna address some of the cryptography protocol, the protocol that's used for this area of your infrastructure solution. So if you're using database when you're retrieving data, you can use private information retrieval, your PIR. This allows you to access sensitive data in the database. So this can be implemented if you have database that contains sensitive data. And then you have another protocol called Secure Function Evaluation, your SFE. It has two separate input that require from any, right? And so the example that they have here is that you have someone that's doing statistic analysis for study habits. I've done this before for my trends on Amazon over the last 5 years, right? Apply it to machine learning and see what product I buy the most. Guess what product I buy the most?
Give me a hint.
Coffee.
No, I don't drink coffee. Cat beds and moisturizer. So I did an analysis from COVID time up until last year, right? And Amazon spits out the data. You can obtain your data, how much you spend and all of that. And then I apply it to a function to be able to analyze like my trend, right? And you can approach it with different functions from linear algebra to be able to analyze like, you know, how much I spend, what kind of products I buy the most, right? And sure, it spits out, you know, but the data from Amazon, you have to, there are blank cells too, so you have to give it arbitrary data, like you gotta plug in the zeros and things like that. So that's part of like the big data engineering. But yeah, so something like that would be, you know, if you're using, you know, analysis like this and you want to be able to determine and compare like the two stores, like let's say that Amazon compared to Walmart.com or something like that, that will be something that you can consider for the input for but you want secure, right? So you can do function evaluation for the query in the two organization for statistical analysis. So if your data is sensitive, you want to compare from two location, you can use SFE, right? I can do that with my Amazon data that it may be highly sensitive compared to another retailer, and so on. Okay, and then we have private function evaluation, your PFE. This is multi-party computation, your MPC. It allows multiple inputs, so more than two, right? So that way you can calculate and to be able to perform. So when you're dealing with more privacy or private data from different locations, or you need to be able to calculate it, you should use your private function evaluation. So earlier we talked about how IPsec is used for VPN. How does IPsec secure data transmission in VPN? It uses MAC, which is a hashing technology. Symmetric encryption for data, right? Uses the same key to encrypt and decrypt, and then asymmetric encryption for key exchange. Oh, and if I forgot to touch on 15, the function of homomorphic encryption, that allows computations on encrypted data without decrypting it, protecting the sensitive data during the doing processing. So if you have data in use, right, it doesn't have to decrypt it to protect it. So in comparison between cipher that is stream and block cipher, stream cipher encrypt data 1 bit at a time, as I mentioned that earlier. That will be ideal for real-time or web-based type of application. And then you have block cipher, which encrypts on fixed size block where it chunks, right? Think of it like group of bits, or certain size in your data is going to be chunked up, and it's going to encrypt each chunk, so each block. And the block cipher often would give you more robust security, but slower, right? Compared to stream, which is closer to real time, faster. Any question? Okay, for 18, it asks about deep fake. So let's go back to our notes here. So here, there's one section that's not included in your, this one doesn't include it in your assignment. So biometric impersonation, right? This is getting to be kind of popular because I think now that we are in transition to move away from password and using biometric as another factor in authentication. So as it is, right, people also use voice to authenticate, right? Fingerprints, gait, etc. But you probably know about deepfake, right? Deepfake is a way that we can use deep learning to be able to make things that look realistic where it is not, it is fake, right? Such as people's voice, people's face, like you getting a phone call from your loved ones to ask you to do a Zelle of $500 into their mobile number. And it might sound like your family member, it might look like your family member, but it's not, right? Yeah, yeah, prisons. So there are a lot of criminal activity in this area now. I think North America, we are getting to be kind of closer to that. But this has been growing rapidly in other part of the world, like in other continents. So you will see more of it surfacing in the scam that, you get phishing voicemail and phishing calls, right? You're gonna see a lot of deep fake in those phishing calls too. So, if we use technology like machine learning and deep learning for the greater good, right, it can go the other way as well. So deep learning uses AI and neural networks. We see a lot of this now. So when you're looking at deep fake, it can be used to impersonate someone. And I think you saw that with the FBI, right? The FBI, they said that how long did it take? How long did it take for deep fake? How long of your voice that I need? 30 seconds of your voice recording. That's all I need, right? It doesn't have to be minutes. And so if someone have a recording of a voice, someone's voice for 30 seconds, they can take that, put it through the algorithm, be able to spit out your actual conversation, right? It's scary now that you think about it becoming all the YouTube videos and all the things that you release.
Celebrities and make it seem like they said something in interviews when they really didn't.
Yeah,
That's like the most common thing I see on social media.
yeah. So
It
it's,
looks so real too.
and soon enough, that's gonna be integrated with an app, right? For someone to make a video, so yeah, and the way that we scale technology, so you can see that the fluidity of this particular field, it's always changing, right? 1 year it's like this, and then next year that's old news, something else is gonna come through. trying to prevent that, but something else is gonna pop up. So it's gonna keep you on your toes. But it's very interesting on how technology changed the way we communicate, and with that, it changes the landscape in security, um, and how we protect our systems and people and resources, right? So very, very cool. I think it's cool. Okay, so another area that we need to pay attention to is your 3D printing. As 3D printing is becoming more popular, you can definitely build a 3D printer. You can you can use 3D printing to print artificial biological parts. You know, I know the makerspace here, I Make Innovation Center, they have great 3D printer now. We had replaced a lot of them. So you can use it for hobbies, you can use it for, you know, prototyping, you can do a lot of things with 3D printing. It's very cool. Just have to have a little bit of knowledge in design and design concept to be able to draw and create whatever art or things that you want to print. But 3D printing becomes a security issue for us. Why? Because it is connected to the network. It can be pre-scheduled and preset to print. And so therefore it becomes a problem, right? When we say a problem, that doesn't mean that we don't use it. We just got to make sure that we secure it. Okay, so let me move 17 down in case we're still looking at that, right? So for 18, it says, why is deepfake technology considered a security threat? It's because that can be used to impersonate someone's voice, appearance, or for criminal activities, like identity theft, fraudulent activity, unauthorized access. If you use voice command to access your home, right, that can be a problem. So that means that when we're using biometrics with multi-factor, we need to think about multiple ways to use biometric, fingerprint and voice, facial recognition, voice, and something else, right? So just like everything else that we use, there gotta be validity in how we access the system. That means that we have to make sure that we validate our identity, right, multiple ways. And that's really truly multi-factor, I think. Right. Okay. So for the CNSA suite, how this play into cryptography is it is a set of standards that's used for top secret communication, right? And that is going to be updated to counter potential quantum quantum computing attempt to break cryptography. So they already have the countermeasure for that, right? Because we are looking at how computing technology will change in the landscape of security. If someone can get a hold of a quantum system, they can apply, or or they can use AI, they can use all of this technology. How are we going to be able to prevent that? So this suite in particular is going to help reduce, can't say remove, reduce the risk of the usage in quantum computing for threats. And then lastly, your 3D print. So explain how 3D printing is a security risk. Hackers can tamper with the network using 3D printer connection. Just like your wireless printer or any form printer, right? Anything that's connected to the network can be an entry point to your network. You just got to make sure that you secure all your endpoints. That's the goal. They can use it to steal intellectual property, because we can, let's say that I am prototyping my products. When I 3D print, I need to load the file into the 3D printer. 3D printer have RAM and storage to be able to accommodate design for 3D print. So someone can access the storage to be able to obtain my prototype design. And then that can also lead to theft of IP, intellectual property. And then you can have unauthorized reproduction, and you see unauthorized reproduction all the time. The generic things that you buy that looks real, right? Let's say that I want to buy a fake Levi's jacket. It looks like a real Levi's jacket, but it's not, or fake Converse shoes. You've seen these, right? Sometimes companies will pursue legal actions to, vendors that create that. Um, when I was in high school, one of my close friends' father, he was specialized in this area. He would go to conventions for shoes. He's paid by a company that would go and look at design for the new shoes, expensive new shoes, and then take that design and come back to the company and replicate something similar for a lot less and be able to sell more, right? So, you have people that are in the business for that, right? So this is why you would see technology like 3D printing become a flaw in production or manufacturing. Right? So we have to protect the resource. It doesn't mean that we don't use the resource. We just need to protect the resource. Okay. A kind of cool chapter. I enjoy it. A lot of it is reviewing. I know that you know some of those terms when you study for Security Plus, but it also presents to you different additional angles on how security is lacking or improve in some area. Okay, let me stop recording.